Have you ever gazed at the pitch-black sky and wondered what still lies beyond? What if I tell you that there are many things that are still unknown, even to the rest of the universe? Let's go into the greatest mysteries of the universe and its wonders. These cosmic enigmas, such as the indistinct dark matter and the infinity black holes, fascinate us and stretch our brains so much. What is the importance of uncovering these mysteries? In exploration of these mysteries, there is promising dominance. The better we comprehend the universe, the better place we occupy in the whole thing. Ready, go, as this is a cosmic journey. Who knows where the truth is? What caused the Big Bang? Imagine standing in the middle of a quiet, dark room, feeling the weight of stillness all around you. Now picture that same room filled with an endless sea of stars, swirling galaxies, and colorful nebulae. A cosmic ballet of creation. All of this splendor had a humble beginning, a moment that changed everything. The Big Bang, around 13.8 billion years ago. Everything we see and know, from the tiniest particles to the grandest galaxies, was squeezed into a single, infinitesimally hot and dense point. It's almost unfathomable, isn't it? One moment, this point sat in silence. The next, it erupted in a magnificent explosion, unfurling the fabric of space and time as we know it. But what, you may wonder, sparked this monumental event? Let's dive into one of the theories that offer a glimpse into this mystery: the idea of quantum fluctuations. Picture the universe as a giant cosmic pot of boiling soup. In this pot, there are moments of chaos, tiny bubbles of energy popping in and out of existence. Some scientists propose that our universe was born from one such bubble, a fluctuation in what we call a quantum vacuum. In this state of nothingness, a random event caused a monumental explosion, giving rise to everything we now see around us. Imagine the universe as a delightful accident emerging from chaos, a reminder of how unpredictable existence can be. But what if the Big Bang wasn't the beginning at all? Another intriguing possibility is that our universe is part of a grand cycle, going through endless loops of expansion and contraction. Some scientists believe we've experienced many Big Bangs before this one, each a fresh start after a cosmic collapse. Picture it like a cosmic heartbeat, where the universe expands and then compresses, creating a never-ending dance of birth and rebirth. Isn't it fascinating to think that what we see today may just be the latest act in a cosmic play that has been running for eons? As we explore deeper, we stumble upon an even more profound question. Did the Big Bang mark the beginning of time itself? Imagine a realm where the very concept of before didn't exist. A strange idea, right? In this pre-Big Bang world, traditional notions of time and space may not have applied at all. If time truly began with the Big Bang, could it also meet an end someday? These ponderings tickle our imaginations, urging us to explore the great unknown. Each question about our universe sparks curiosity, reminding us of the vastness of what we have yet to uncover. As we gaze into the night sky, let's hold on to the wonder that our universe, with all its beauty and complexity, may have originated from a tiny speck in the fabric of existence. So, next time you look up at the stars, remember, you're not just seeing distant suns. You're witnessing the remnants of a colossal explosion that began it all, a story that continues to unfold. The nature of dark matter. As we gaze up at the night sky, we can't help but be enchanted by the twinkling stars and the beautiful glow of distant galaxies. But did you know that there's a vast, mysterious part of the universe that remains hidden from our eyes? This elusive substance is called dark matter, and it plays a crucial role in the cosmos, even though we can't see it or touch it. So, what exactly is dark matter? Well, imagine trying to find a ghost in a dark room. You can't see it, but you can sense its presence. Dark matter is like that ghost. It doesn't emit, absorb, or reflect light, which makes it completely invisible to our telescopes. But just because we can't see it, doesn't mean it isn't there. Astronomers have become skilled detectives, piecing together clues to deduce the existence of dark matter. One of the most fascinating pieces of evidence comes from the way galaxies behave. When scientists observe galaxies, they notice something strange. They spin at such high speeds that, without the extra gravitational pull of dark matter, they should tear themselves apart. Think of it this way. If you were spinning a pizza dough in the air, it would fly apart if you didn't have your hands holding it in place. Dark matter acts like an invisible hand, holding galaxies together and providing the necessary gravitational glue to keep them intact. This unseen mass forms the very framework of our universe, helping to shape everything we see around us. Now, you might be wondering just how much dark matter is out there. Scientists believe it makes up about 27% of the total mass energy content of the universe. That's a huge chunk. And yet, despite its significance, we still haven't directly detected dark matter. It's as if we're trying to find a treasure chest, buried deep underground without knowing its exact location. Various theories have emerged to explain what dark matter could be, ranging from weakly interacting massive particles to axions and sterile neutrinos. Each of these ideas presents exciting possibilities, but they also come with their own sets of challenges. Imagine embarking on an intergalactic treasure hunt, where each clue leads you down a new path filled with tantalizing hints and unexpected twists. Some scientists have launched experiments deep underground or high in the sky, searching for dark matter particles as if they were precious gems hidden among the stars. What if one day we finally uncover the true nature of dark matter? It could open new doors in physics and help us understand the very fabric of our universe. Every failed experiment might feel like a setback, but it's essential to remember that each attempt brings us one step closer to discovery. The quest for dark matter is not just about finding answers. It's about igniting our curiosity and inspiring future generations of scientists and explorers. As we ponder the mysteries of dark matter, we realize that this hidden universe is just as important to the story of creation as the stars we can see shining in the night sky. So the next time you look up at the stars, take a moment to appreciate the incredible universe that lies beyond our sight. There's so much more happening up there than meets the eye, and the secrets of dark matter are just waiting to be uncovered. Who knows what wonders we'll find as we continue our journey through the cosmos? The mystery of dark energy. While dark matter presents us with a fascinating puzzle, dark energy is a whole different enigma that adds another layer of complexity to our understanding of the universe. Imagine standing on a beach, watching the waves come in and recede. Now picture not only those waves continuously crashing, but also a powerful tide pulling them back with increasing strength. That's a bit like what's happening with our universe. Not only is it expanding, but it's actually accelerating in that expansion. This mysterious force driving galaxies apart is what we call dark energy. In fact, dark energy is believed to make up about 68% of the entire universe. This means that most of the cosmos is shrouded in mystery, beyond what we can see or understand. But what exactly is dark energy? One of the leading theories suggests that it could be a fundamental property of space itself, known as the cosmological constant. This idea was introduced by the brilliant physicist Albert Einstein in his equations for general relativity. Imagine that even the emptiest space is not truly empty. It possesses a certain energy density that causes it to expand. Just as a balloon stretches when air is added, this constant energy pushes the fabric of the universe outward. However, there's another intriguing possibility. What if dark energy isn't just a constant, but a dynamic field that changes over time? This concept is called quintessence. Think of it like a river that flows and shifts, affecting the landscape around it. If dark energy behaves this way, it could mean that the forces driving our universe's expansion are not fixed. but rather in constant flux, influencing how galaxies move apart over time. The implications of dark energy are staggering and provoke many questions about the long-term fate of our universe. As this mysterious force pushes galaxies to drift further away from one another, what will happen to them? Will they become so isolated that they lose connection with each other, like ships sailing off into the horizon? And what about the stars? As galaxies drift apart, will they eventually burn out, leaving behind a dark, cold universe, devoid of light and warmth? Imagining a future like this can be unsettling. It raises profound questions about our cosmic destiny. The quest to understand dark energy is crucial not only for grasping the current state of our universe, but also for contemplating where it is all headed. Are we witnessing the beginning of a universe that expands forever? Or will dark energy change course, leading to a different fate? As scientists continue to explore the mysteries of dark energy, they are piecing together a narrative that could reshape our understanding of existence itself. Each discovery serves as a reminder of how much we have yet to learn about the cosmos and our place within it. So, as you look up at the night sky, remember that beyond the twinkling stars lies a universe driven by forces we are just beginning to comprehend. The story of dark energy is a reminder of the beauty of exploration and the infinite wonders of the universe waiting to be discovered. Are we alone in the universe? The question of whether we are alone in the universe resonates deeply within us, stirring our curiosity and imagination. As we gaze up at the night sky, filled with countless stars, it's hard not to wonder. With billions of galaxies, each containing millions or even billions of stars, could there be other intelligent life out there? This tantalizing thought invites us to explore the cosmos and consider the possibilities of existence beyond our Earth. This exploration leads us to a fascinating conundrum known as the Fermi paradox, named after the renowned physicist Enrico Fermi. He famously posed the question, where is everybody? Given the vastness of the universe, one would expect to see signs of extraterrestrial civilizations. Yet, our extensive searches for intelligent life have yielded little to no evidence. This paradox ignites endless debate and speculation among scientists, philosophers, and dreamers alike. One compelling possibility is that intelligent life is exceedingly rare. The rare Earth hypothesis suggests that the specific conditions that allowed life to thrive on Earth are so unique that the emergence of complex life forms may be an extraordinary anomaly. Think about it. Our planet is perfectly positioned in the Goldilocks zone, where temperatures are just right for liquid water to exist, and it has the right mix of elements and environmental stability that foster life. In such a vast universe, it's plausible that Earth-like conditions may be a rarity, making intelligent life an unlikely occurrence elsewhere. On the flip side, there's an intriguing theory that advanced civilizations might indeed exist, but are deliberately avoiding us. This is sometimes referred to as the zoo hypothesis. According to this idea, extraterrestrial beings might be observing us from afar, much like zookeepers watching over animals in a habitat, choosing not to make contact. Perhaps they're waiting for us to reach a certain level of technological or social maturity before they introduce themselves. This notion tantalizes the imagination, offering a glimpse of a universe filled with life but governed by a mysterious code of conduct. In the quest for answers, scientists have turned their attention to the search for extraterrestrial intelligence. Using powerful radio telescopes, they scan the skies for signals from other worlds, listening for beeps and blips that could be communication attempts from distant civilizations. Each faint whisper of a signal brings a rush of excitement and hope, igniting our ambitions to connect with life beyond our planet. Imagine receiving a message from a far-off galaxy, containing thoughts and experiences from beings who share our desire for understanding and connection. The possibilities are thrilling and inspiring, pushing us to explore the cosmos with renewed vigor. As we ponder this profound question, we are reminded of our place in the vast universe. The search for extraterrestrial life is not solely about discovering others. It's also about understanding ourselves and our shared existence within this grand cosmic tapestry. In our quest to find out if we are alone, we reflect on what it means to be human, our dreams, fears, and aspirations. Are we the only ones looking up at the stars and wondering what lies beyond? As we continue to explore the mysteries of the universe, we remain united in our curiosity and hope. Whether or not we ever discover other intelligent life forms, the journey itself enriches our understanding of the cosmos and our role within it. So, the next time you find yourself gazing at the night sky, take a moment to consider the countless possibilities that lie beyond. The universe is vast and mysterious, and while we may not have all the answers, our quest for knowledge continues to illuminate the path ahead. The multiverse hypothesis. What if our universe is just one of many? This exciting idea is known as the multiverse hypothesis, which suggests that there could be countless other universes, each with its own unique set of physical laws and constants. Some of these universes might look a lot like ours, while others could be incredibly different, with alternate realities waiting to be discovered. Just think about it. The possibilities are practically limitless. The concept of the multiverse springs from various branches of physics, including quantum mechanics and cosmic inflation. To understand how these ideas come together, let's first dive into quantum mechanics. In this field of science, there's a fascinating concept called superposition. It tells us that particles can exist in multiple states at once. Imagine flipping a coin. While it's in the air, it's not just heads or tails, it's in a state of both. Now apply this to the universe. If every possible outcome of every event exists in its own separate universe, that means every decision you've ever made could branch off into its own reality. For example, think about a simple choice, like what to have for breakfast. In one universe, you might have chosen pancakes, while in another, you opted for cereal. In yet another universe, perhaps you decided to skip breakfast entirely. Each of these decisions creates a new branch in the vast tree of the multiverse, leading to a plethora of different outcomes and experiences. The idea of cosmic inflation also supports the notion of the multiverse. Shortly after the Big Bang, the universe experienced a brief period of rapid expansion known as inflation. During this time, different regions of space could have inflated at different rates. This uneven expansion might lead to a patchwork of universes, each with its own distinct characteristics. Picture a balloon being blown up unevenly, where some parts expand more than others, creating different shapes and sizes. Each of these regions could become its own universe, with different rules governing how things work. While the multiverse hypothesis may sound like something out of a science fiction novel, it raises profound questions about the nature of reality. If there are indeed infinite universes, what does that mean for our understanding of existence? Are we merely one of countless variations of ourselves living out different lives in parallel universes? This idea invites us to explore deeper philosophical questions about identity, choice, and the nature of the cosmos. The vastness of the multiverse encourages us to dream big and think outside the box. It reminds us that our understanding of the universe is still in its infancy. As we continue to explore the mysteries of space, we may uncover more evidence that supports the existence of multiple universes. Whether or not we ever prove the multiverse hypothesis, the mere contemplation of it sparks our imaginations and encourages us to ask even bigger questions about our place in the cosmos. So, the next time you look up at the stars, consider the possibility that each twinkle might be a gateway to another universe, a world where things could be very different from our own. The multiverse is not just a scientific theory, it's an invitation to explore the infinite wonders of reality itself. the fate of the universe. As we gaze into the future, we're confronted with a profound and awe-inspiring question. What will happen to the universe? Will it continue to expand forever, collapse in on itself, or meet a different fate entirely? The destiny of the cosmos hinges on a variety of factors, including the enigmatic forces of dark energy, the density of matter, and the fundamental forces that govern the universe's behavior. One of the most widely discussed scenarios is known as the Big Freeze. In this vision of the future, the universe continues to expand indefinitely, driven by the mysterious force of dark energy. Over trillions of years, stars will eventually burn out, their brilliant light extinguished, and galaxies will drift apart like lonely islands in a vast cosmic sea. As time marches on, the universe will grow dark and cold, transforming into a desolate wasteland devoid of life and light. This haunting end evokes powerful images of a universe where nothing but silence remains, a chilling reminder of the ephemeral nature of existence. But there's another possibility, the Big Crunch. In this scenario, the expansion of the universe could eventually reverse itself, causing everything to collapse back into a singularity, a point of infinite density and heat. The dramatic end of the universe would be a spectacular sight, but it also raises profound questions about what might follow. Could this collapse lead to a cycle of rebirth, where the universe implodes only to explode once again in a new Big Bang, giving rise to another universe? Imagine a cosmic cycle where life, death, and rebirth dance through time, hinting at a grand design that stretches far beyond our comprehension. Then we have the more catastrophic scenario, known as the Big Rip. In this unsettling vision, the expansion of the universe accelerates to such a degree that it tears apart galaxies, stars, planets, and even atoms. The thought of the universe being violently ripped apart is both terrifying and fascinating. It paints a picture of a universe that is not only alive, but also dynamic and ever-changing, constantly reshaping itself in ways we can hardly imagine. Each of these scenarios offers a glimpse into the potential futures of our universe, but regardless of what ultimately unfolds, contemplating the fate of the universe connects us to our place in the vast tapestry of time and space. It serves as a poignant reminder of our fleeting existence within this grand cosmic narrative. As we ponder these possibilities, we are encouraged to reflect on our lives and the choices we make. In a universe that may one day be devoid of light and life, how do we find meaning in the present? What legacy do we wish to leave behind? Each moment we share, each story we tell, contributes to the intricate fabric of existence, no matter how small it may seem in the grand scheme of things. The singularity inside black holes. Black holes are among the universe's most fascinating and perplexing phenomena, captivating the imaginations of scientists and enthusiasts alike. These cosmic enigmas form when massive stars exhaust their nuclear fuel and undergo gravitational collapse. The result is a region of space where gravity becomes so intense that nothing, not even light, can escape. At the very core of a black hole lies the singularity, a point where the laws of physics as we understand them cease to function. In this infinitely dense and minuscule state, matter is compressed to an unimaginable extent, creating conditions that challenge the very foundation of our scientific principles. The singularity represents a realm where space and time intertwine in ways that defy our conventional understanding, making it one of the most mysterious aspects of the cosmos. Surrounding the singularity is a boundary known as the event horizon. This boundary serves as the ultimate point of no return. Once anything crosses it, whether it be gas, dust, or even entire stars, it is irretrievably pulled into the black hole. The event horizon creates a stark contrast between what we can observe from the outside and what exists within. It acts like a cosmic trapdoor, rendering the interior of the black hole completely inaccessible to outside observers. This has led to profound questions about the fate of matter and information that crosses this boundary, as well as the nature of reality itself. Inside a black hole, the behavior of space-time is thought to differ dramatically from our everyday experiences. Some theories suggest that within the event horizon, the gravitational forces might warp space-time to such an extent that distances and the flow of time become distorted. In this bizarre environment, time may slow down relative to the outside universe, leading to the strange possibility that events inside a black hole could appear to happen at a different pace. This warped perception of time and space raises tantalizing questions about the fundamental nature of existence and how we perceive reality. One of the most intriguing discussions in theoretical physics revolves around the black hole information paradox. This paradox questions whether information about objects that fall into a black hole is truly lost forever, or if it can somehow be retrieved. According to classical physics, once something crosses the event horizon, all information about it vanishes, which contradicts the principles of quantum mechanics that state information must always be conserved. This contradiction has sparked intense debates and research within the scientific community, as resolving this paradox could lead to revolutionary insights about the underlying principles of the universe and the very fabric of space-time. The study of black holes and their singularities pushes the boundaries of human understanding and compels us to confront some of the most profound mysteries of existence. As researchers continue to explore these enigmatic cosmic structures, we are gradually unraveling the secrets of the universe and gaining deeper insights into the fundamental forces that shape our reality. Each discovery brings us closer to understanding not only the nature of black holes, but also the broader implications for our comprehension of space, time, and the universe as a whole. The quest to unlock the mysteries of black holes continues to inspire curiosity and exploration, reminding us of the vast unknowns that still lie beyond our reach. What lies beyond the observable universe? The observable universe is an astonishing expanse, stretching approximately 93 billion light-years in diameter. Within this immense region, we can observe countless galaxies, stars, and cosmic phenomena. However, what lies beyond this observable frontier remains one of the most tantalizing mysteries of modern cosmology. The fundamental question arises: are there regions of space that we can never see, no matter how advanced our technology becomes? This inquiry invites us to contemplate the limits of human understanding and the very nature of the universe itself. Beyond the observable universe, there exists the possibility of an infinite expanse of space that extends far beyond the cosmic horizon we can detect. This cosmic horizon marks the boundary of our observable universe, defined by the finite speed of light and the age of the universe. Since the Big Bang, light from regions beyond this boundary has not had enough time to reach us. While we can hypothesize about what might exist beyond, we remain incapable of directly observing it, leaving us with only speculation and imagination. Some scientists propose that the regions beyond the observable universe could be populated with galaxies, stars, and cosmic structures similar to those we see within our own cosmic bubble. This perspective suggests a continuity of the universe beyond what we can currently perceive. Others, however, speculate that the physical laws and constants governing these distant regions might differ significantly from those we are familiar with, leading to entirely unique phenomena. This notion brings us back to the concept of the multiverse, a theoretical framework where multiple universes exist, each with its own distinct properties and rules, creating a rich tapestry of realities that coexist alongside one another. The ongoing expansion of the universe adds yet another layer of complexity to this enigma. As space itself expands, the distant galaxies we currently observe will eventually recede beyond our reach. In fact, due to the expansion of space, some galaxies will move away from us faster than the speed of light, rendering them invisible to our telescopes. Over time, this process will result in an ever-shrinking observable universe, leading to the sobering realization that we may eventually find ourselves isolated in our own cosmic bubble, cut off from the vastness that lies beyond. Imagining what exists beyond the observable universe challenges our perception of reality and compels us to explore the infinite possibilities that the cosmos may hold. Even if we cannot see what lies beyond, the very act of questioning stimulates our curiosity and drives scientific inquiry. It serves as a reminder that the universe is far larger and more mysterious than we can comprehend, urging us to push the boundaries of our knowledge and to explore the depths of existence. In our quest for understanding, we may discover that the universe's true nature is even more astonishing than we can currently imagine. What is time? Time is a concept that we all know intuitively, yet struggle to define. Every day we mark our existence in seconds, minutes, hours, and years. But have you ever paused to wonder what time really is? How did it come to be? And could it ever cease to exist? For centuries, philosophers, scientists, and curious thinkers have pondered these questions, seeking to peel back the layers of one of life's most profound mysteries. One of the most widely accepted theories suggests that time began with the Big Bang. Imagine this. Before the universe erupted in a cataclysm of energy and matter, there was no time at all. Just a singular, undifferentiated state of existence. It's as if the cosmos held its breath, waiting for the moment to unfold. As the universe expanded and cooled, time emerged, a fundamental thread woven into the very fabric of reality. This begs a tantalizing question. If time had a beginning, does it also have an end? Some scientists and thinkers propose that our perception of time may not be as straightforward as we believe. Instead of flowing in a neat, linear path from past to present to future, time might be more like a sprawling landscape where all moments exist simultaneously. This idea draws on principles from quantum mechanics, where particles can occupy multiple states at once, challenging our understanding of time. Could it be that our linear experience of time is simply a byproduct of our limited consciousness, a way for our minds to make sense of the chaos of existence? Adding another layer to this enigma is the concept of time dilation, which tells us that time doesn't tick away uniformly across the universe. According to Einstein's theory of relativity, time can stretch and contract depending on the gravitational field and the speed at which an observer moves. Picture yourself on a spaceship traveling near the speed of light. Time would flow differently for you compared to someone remaining on Earth. This incredible phenomenon reveals that time is not a static backdrop to our lives, but a dynamic dimension that dances and shifts with the universe itself. As we delve into the nature of time, we find ourselves reflecting on our own experiences. Time shapes our memories, fuels our aspirations, and colors our fleeting moments of joy and sorrow. It is a paradoxical force, both personal and cosmic, intertwining our individual stories with the grand narrative of the universe. In this intricate tapestry, time becomes not just a measure of moments, but a profound connection to the very essence of existence. Why does the universe have laws? As we venture deeper into the cosmos, we are inevitably confronted with a compelling question. Why does the universe adhere to laws at all? From the graceful motion of planets in their orbits to the intricate behavior of subatomic particles, everything around us operates according to a set of fundamental physical laws. These laws are not merely arbitrary guidelines. They are precise and universal, underpinning the very nature of reality itself. But why do these laws exist, and what implications do they hold for our understanding of the universe and our place within it. One of the most intriguing concepts related to this question is the fine-tuning argument. This argument suggests that the conditions necessary for life as we know it are incredibly specific. For example, consider the gravitational force that governs the motion of celestial bodies. If this force were even slightly stronger, stars might burn too hot and fast, leaving no time for planets to form and develop life. Conversely, if it were slightly weaker, stars might not ignite at all. Similarly, the strength of the electromagnetic force, which affects how atoms bond and interact, plays a critical role in the formation of matter as we understand it. A tiny variation in this force could lead to a universe devoid of stable atoms, and thus, life itself. This delicate balance raises a profound question. Is this fine-tuning merely a coincidence of chance, or does it hint at a deeper underlying principle governing the universe? One fascinating proposition is that our universe may be just one of countless others in a multiverse. In this vast ensemble of universes, each could operate under different physical laws and constants. Imagine an infinite expanse of realities, some where the laws of physics are dramatically different from our own, and others where conditions are hostile to life. Within this framework, the existence of our life-friendly universe becomes a statistical inevitability, an improbable but fortunate outcome amidst a sea of possibilities. If every conceivable set of physical laws is represented somewhere in the multiverse, our universe's peculiarities may not be so astonishing after all. The anthropic principle adds another layer of complexity to this discussion. This principle posits that the universe must possess the properties necessary for the existence of conscious observers like us to reflect upon it. In simpler terms, if the universe were any different, we might not exist to ask why it is the way it is. This perspective serves as a profound reminder of our interconnectedness with the cosmos. Our very existence is intertwined with the fabric of the universe, suggesting that we are not mere spectators, but active participants in its grand narrative. Exploring why the universe has laws invites us to reflect on our place within this vast expanse. It compels us to consider the intricate balance that governs everything from the tiniest particles to the sprawling galaxies. Each law we uncover, each principle we decipher, reveals a deeper understanding of reality, illuminating the extraordinary mechanisms that sustain the universe. As we continue this journey of discovery, we encounter both awe and humility. The laws of the universe not only shape our physical existence, but also inspire a sense of wonder about the cosmos. They challenge us to seek knowledge, to unravel mysteries, and to appreciate the remarkable interplay of forces that make our lives possible. In this pursuit of understanding, we find ourselves not just observers of the universe, but integral threads in its complex tapestry, each of us contributing to the ongoing story of existence. The cosmic microwave background radiation. As we gaze into the universe, one of the most significant pieces of evidence supporting the Big Bang Theory is the cosmic microwave background radiation. This faint glow of microwave radiation permeates the universe, a relic from the early days of cosmic history. But what does it tell us about the universe's beginnings? The CMB is the afterglow of the hot, dense state of the universe shortly after the Big Bang. As the universe expanded and cooled, photons, particles of light, could finally escape, creating this cosmic radiation. When we observe the CMB today, we're looking at a snapshot of the universe when it was just about 380,000 years old, revealing invaluable information about its early state. The CMB is remarkably uniform, with tiny fluctuations that represent the seeds of future galaxies and structures. Analyzing these fluctuations allows scientists to study the universe's composition, age, and the distribution of matter. The study of the CMB has led to groundbreaking discoveries about dark matter, dark energy, and the overall structure of the universe. However, there are still mysteries embedded within the CMB. Anomalies and unexpected patterns challenge our understanding and prompt further investigation. For instance, why is there a noticeable alignment of certain structures in the CMB? Are these anomalies hints of new physics or remnants of cosmic events we have yet to comprehend? The CMB serves as a bridge between our present and the early universe, inviting us to explore the mysteries of our origins and the evolution of the cosmos. Technology becomes. This question invites us to ponder the limits of our understanding and the nature of the universe itself. Beyond the observable universe, there may be an expanse of space that continues infinitely. Stretching beyond the cosmic horizon we can detect, the cosmic horizon represents the boundary of our observable universe, limited by the speed of light and the finite age of the universe. Light from regions beyond this boundary has not had enough time to reach us since the Big Bang. While we can imagine what might exist beyond, we cannot observe it. Some scientists speculate that the regions beyond the observable universe could be filled with galaxies, stars, and other structures similar to what we see within our cosmic bubble. Others suggest that the physics governing those regions could differ, leading to entirely different laws and constants. This brings us back to the concept of the multiverse, where each universe has its own unique properties, leading to a rich tapestry of realities existing side by side. The expansion of the universe adds another layer to this enigma. As space expands, the distant galaxies we currently observe will eventually recede beyond our reach, moving faster than light, due to the expansion of space itself. Over time, these galaxies will vanish from our view, leaving us with an ever-shrinking observable universe. Will we eventually become isolated in our own cosmic bubble, cut off from the rest of existence? Imagining what lies beyond challenges our perception of reality and compels us to explore the infinite possibilities that the universe may hold. Even if we can't see what lies beyond, the very act of questioning reminds us that the universe is far larger and more mysterious than we can comprehend. The missing baryonic matter. When we gaze up at the night sky, it's easy to become lost in the beauty of the stars, planets, and galaxies that shimmer above us. However, while these celestial bodies captivate our imagination, they represent only a fraction of the universe's composition. The vast majority of the cosmos is believed to consist of dark matter and dark energy, enigmatic forces that shape the universe's structure and expansion. But what about the matter that we do understand? The baryonic matter that forms the stars, planets, and even our own existence. Despite decades of meticulous observations and advanced astronomical techniques, scientists have uncovered a perplexing truth. A significant portion of baryonic matter appears to be missing. In fact, current estimates suggest that we can account for only about 5% of the universe's total mass energy content with baryonic matter. This discrepancy raises a fundamental question. Where is the rest of the baryonic matter hiding? One possible explanation for this missing matter is that it resides in distant galaxies or scattered throughout intergalactic space, existing as a diffuse gas that has eluded our detection. This gas could be incredibly faint, composed of warm or hot ionized hydrogen and helium that emits low levels of radiation, making it challenging to observe with conventional telescopes. Researchers speculate that this diffuse baryonic matter might be spread thinly across vast regions of space, waiting to be uncovered through innovative observational strategies. Another intriguing theory proposes that the missing baryonic matter could take the form of exotic objects, such as primordial black holes or dark stars. These intriguing entities are thought to have formed in the early universe, shortly after the Big Bang. Primordial black holes would be smaller and less massive than the black holes we observe today, making them challenging to identify with current technologies. Dark stars, on the other hand, are hypothetical stellar objects that could emit light only through the annihilation of dark matter particles, further complicating our ability to detect them. The quest to locate this missing baryonic matter invites scientists to refine their observational techniques and theoretical models continually. As new technologies emerge, astronomers are better equipped to probe the depths of space in search of elusive baryonic matter. For instance, advanced radio telescopes are now being developed to detect faint signals emitted by warm hydrogen gas, potentially revealing hidden reservoirs of baryonic matter that have long remained undetected. Each new discovery in this search has the potential to reshape our understanding of the universe and its formation. Uncovering the missing baryonic matter is not just a matter of accounting for the universe's composition. It's a quest that ignites our curiosity and pushes the boundaries of our knowledge. The more we learn about the cosmos, the more we realize how much there is left to explore. This ongoing investigation serves as a reminder that the universe is a vast, mysterious place, full of secrets waiting to be unveiled. As we ponder the nature of baryonic matter, we are also reminded of our own origins. The atoms that make up our bodies, the air we breathe, and the planets we inhabit all stem from this fundamental type of matter. Understanding the fate of baryonic matter not only sheds light on the composition of the universe, but also deepens our connection to the cosmos, reminding us that we are all part of this grand tapestry of existence. The formation of supermassive black holes. Supermassive black holes are among the most fascinating and enigmatic objects in the universe, residing at the centers of nearly all galaxies, including our own Milky Way. These cosmic giants can possess masses billions of times greater than that of our Sun, yet their formation and evolution remain shrouded in mystery. How did these colossal entities come into existence in the early universe, and what processes govern their growth? Their existence not only challenges our understanding of black holes, but also poses significant questions about the evolution of galaxies themselves. Current theories about the origins of supermassive black holes suggest that they may have begun as smaller black holes, formed from the collapse of massive stars shortly after the Big Bang. In the chaotic aftermath of the universe's birth, massive stars would have lived fast and died young, their cores collapsing under gravity's relentless pull. These initial black holes, while small by supermassive standards, could have set the stage for something much larger. Once formed, these primordial black holes had several pathways to grow in mass. One prominent theory posits that they accumulated matter over time, drawing in gas, dust, and even entire stars from their surroundings. As they gobbled up material, their gravitational influence would have increased, allowing them to grow even more. Additionally, black holes can merge with one another, creating more massive entities in the process. The interplay between these mechanisms raises questions about how quickly supermassive black holes could have achieved their enormous sizes. However, the rapid growth of these colossal black holes poses significant challenges for our current models. How could they accumulate such vast amounts of mass in what seems to be a relatively short cosmic time frame? Some scientists propose that supermassive black holes formed in dense environments, such as the centers of early galaxies, where gas and stars were abundant. In these bustling cosmic neighborhoods, black holes could efficiently consume vast amounts of material, facilitating their rapid growth. Another captivating aspect of supermassive black holes is their relationship with their host galaxies. Observations reveal a striking correlation between the mass of supermassive black holes and the characteristics of the galaxies in which they reside. For example, galaxies and their central black holes often grow in tandem, hinting at a profound connection. This raises intriguing questions. Do supermassive black holes influence the formation and evolution of their host galaxies? Or does the evolution of galaxies shape the growth of these black holes? One theory suggests that as a black hole consumes gas and stars, it can affect the surrounding environment, regulating star formation in the galaxy. Powerful jets and winds produced by accreting black holes can blow away gas, preventing new stars from forming and altering the galaxy's evolution. Conversely, the mass and energy generated by stars can impact the growth of the black hole itself. This intricate dance between black holes and their galaxies underscores the interconnectedness of cosmic structures, revealing a dynamic relationship that shapes the universe. As researchers delve into the origins and growth of supermassive black holes, they uncover vital clues about the history of the universe and our own galactic home. Each discovery not only enhances our understanding of these enigmatic giants, but also ignites our imagination and wonder. The quest to understand supermassive black holes is not just a scientific pursuit. It is a journey into the very heart of the cosmos, illuminating the processes that govern the evolution of galaxies and the universe itself. In this ongoing exploration, we are reminded of the vastness and complexity of the universe we inhabit. The formation of supermassive black holes challenges us to rethink our understanding of space and time, urging us to confront the mysteries that still lie beyond our grasp. As we seek answers to these profound questions, we become part of a grand narrative that connects us to the universe, fueling our desire to learn more about the cosmic wonders that surround us. The structure of the universe. When we look at the night sky, we are impressed by the beauty of the many stars and galaxies. Have you ever pondered how all of these celestial characteristics came to be? The universe's structure resembles a huge jigsaw composed of galaxies, stars, and other cosmic phenomena. This complicated network did not emerge by coincidence. Rather, it resulted from a combination of gravitational forces, dark matter, and the circumstances established by the Big Bang. Galaxies aren't scattered randomly across space. They actually form a vast network known as the cosmic web. Think of this web as a giant spider's web stretched across the universe. It consists of long, thin strands made up of galaxies and clusters of galaxies, all connected by dark matter. Between these filaments are huge empty spaces known as voids. The formation of this cosmic web is an ongoing process. Over billions of years, gravity pulls galaxies together, causing them to cluster and form these structures. Just like how raindrops collect in puddles, galaxies group together due to gravitational attraction. To understand how this all works, scientists use computer simulations. These simulations act like virtual laboratories, modeling how gravity, dark matter, and gas interact over time. By running these simulations, scientists can visualize how galaxies come together, evolve, and shape the universe. It's like watching a time-lapse video of the universe's history. Current observations reveal that some of the largest structures we see today, like galaxy clusters and superclusters, formed when smaller galaxies merged and interacted with each other. This process of coming together and changing is what drives the evolution of the universe's structure. Exploring the structure of the universe is a journey that inspires awe and wonder. It reminds us of how everything is interconnected, from the tiniest particles to the biggest galaxies. As we learn more about these cosmic structures, we also uncover the story of our universe, highlighting the beautiful complexity of existence itself. The mystery of time travel. Time travel is one of the most fascinating ideas in both science fiction and theoretical physics. Just imagine being able to jump into a time machine and visit the past or the future. This captivating concept sparks our imagination and raises intriguing questions about the very nature of time itself. But can we really travel through time? Or is it just a fantasy? To understand the possibilities of time travel, we first need to look at Einstein's theory of relativity. This groundbreaking theory suggests that time is not a fixed thing. Rather, it's connected to space, forming something called space-time. Imagine space-time as a stretchy fabric that can bend and warp. According to this theory, if we could travel close to the speed of light or find a way to navigate through hypothetical wormholes, we might be able to manipulate time in ways that could make time travel possible. Now let's talk about wormholes. These are theoretical tunnels that could connect two distant points in space-time, like a shortcut through the universe. If wormholes exist, they could potentially allow us to travel to the past or the future in a fraction of the time it would normally take. However, using a wormhole for time travel comes with a lot of challenges. For instance, we don't yet know if they're stable or even if they exist at all. Plus, there are many complex problems to solve, including the risk of paradoxes. One of the most famous time travel paradoxes is the grandfather paradox. Picture this. If a time traveler goes back in time and accidentally prevents their grandfather from meeting their grandmother, would that time traveler even exist anymore? This paradox raises big questions about causality, the cause and effect relationships that define our reality. If we change something in the past, what happens to the present and future? Despite these mind-boggling challenges and unanswered questions, the concept of time travel continues to intrigue scientists, writers, and dreamers alike. It pushes us to think about the possibilities of bending the rules of reality and explores the depths of our imagination. As we ponder time travel, we delve into profound questions about existence, free will, and the very fabric of the universe. In our quest to understand time, we not only confront the mysteries of the cosmos, but also reflect on our own experiences. How do we perceive time? Why does it sometimes feel like it flies by, while at other times, it drags on? The allure of time travel invites us to explore these questions, reminding us that, while we may not have a time machine just yet, the wonders of time and space are vast and full of potential. The role of quantum mechanics. We come across the peculiar and intriguing world of quantum physics as we go further into the domain of the very tiny. This area of physics challenges our traditional view of the cosmos by revealing often surprising realities. It presents concepts such as superposition, entanglement, and the elusive nature of particles, making us wonder, how does the cosmos function according to quantum physics? At the heart of quantum mechanics is the idea that particles can exist in multiple states simultaneously, a concept known as superposition. Imagine flipping a coin. While it's spinning, it's neither heads nor tails, but a blend of both possibilities. It's only when we observe the coin that it decides on one outcome. This principle raises profound questions about the nature of reality. Does our observation affect the outcome of events in the quantum world? Entanglement, another puzzling aspect of quantum mechanics, reveals that particles can become intertwined in such a way that the state of one instantly influences the state of another, regardless of the distance between them. This phenomenon baffled even Einstein, who famously referred to it as spooky action at a distance. The implications of entanglement challenge our understanding of locality and causality, leading to deep philosophical inquiries about the interconnectedness of the universe. Moreover, the quest to unite quantum mechanics with general relativity, Einstein's theory explaining gravity, has become one of the greatest challenges in modern physics. While both theories have proven remarkably successful in their respective realms, merging them into a single framework remains elusive. Some theories, like string theory, propose that the fundamental building blocks of the universe are not point-like particles, but rather tiny, vibrating strings, potentially providing a bridge between the quantum world and the cosmos. As we explore the role of quantum mechanics, we are reminded that the universe is far stranger than we can imagine. This interplay of the very small and the vast cosmos invites us to reflect on our understanding of reality and the profound mysteries that lie at the heart of existence. Why is the universe so big? One of the most awe-inspiring questions about the cosmos is, why is the universe so big? The sheer vastness of space, filled with countless galaxies, ignites a sense of wonder and curiosity within us. To understand this monumental scale, we must journey back to the very beginning of the universe, a moment known as the Big Bang. The Big Bang marks the moment when our universe sprang into existence approximately 13.8 billion years ago. In the aftermath of this cataclysmic event, the universe began to expand rapidly. This initial expansion was not just a slow stretching of space, but a phenomenal explosion of growth known as cosmic inflation. During this brief period, which lasted only a fraction of a second, the universe underwent an exponential expansion, growing from subatomic scales to sizes far larger than we can comprehend. Imagine blowing up a balloon. As you inflate it, the surface expands rapidly in all directions. This analogy captures the essence of cosmic inflation, where the fabric of space itself stretched beyond our wildest imagination. The implications of this incredible expansion are profound. Cosmic inflation not only laid the groundwork for the formation of galaxies, stars, and planets, but also significantly influenced the universe's overall structure. As the universe expanded, tiny fluctuations in density began to emerge. These variations served as the seeds for the formation of galaxies, clustering together under the influence of gravity to create the complex structures we observe today. One of the remarkable remnants of this early period is the cosmic microwave background radiation. This faint afterglow of the Big Bang still permeates space, providing us with a snapshot of the universe when it was just 380,000 years old. By studying the CMB, scientists can glean invaluable insights into the conditions that shaped our universe and the processes that led to its vastness. Despite our attempts to grasp the scale of the universe, its enormity remains challenging to fathom. The observable universe stretches approximately 93 billion light-years across, filled with billions of galaxies, each housing billions of stars. To put this into perspective, 1 light-year, the distance light travels in a year, is about 5.88 trillion miles, 9.46 trillion kilometers. This staggering distance makes it nearly impossible for us to truly comprehend the vastness of space. But even more mind-boggling is the realization that the universe may extend far beyond what we can observe. Is it infinite, or does it have defined boundaries? Scientists continue to ponder this question, recognizing that there is still so much we do not understand about the cosmos. As we contemplate the immense size of the universe, we are reminded of our place within it. We are but a tiny speck in this cosmic ocean, yet our quest for understanding connects us to the stars and fuels our exploration of the mysteries that lie beyond. The vastness of the universe invites us to consider the unknown, what lies beyond the observable limits, and what wonders await discovery. This quest for knowledge not only enhances our understanding of the universe, but also reflects our innate curiosity and desire to explore. It reminds us that while we may be small in the grand scheme of things, our capacity to question, learn, and reach for the stars is a testament to the remarkable spirit of human exploration. As we gaze into the night sky, we are encouraged to keep wondering, keep seeking, and keep expanding our understanding of this incredible universe we inhabit. The nature of gravity. When we think of gravity, our minds often conjure up images of being firmly anchored to the ground, of apples falling from trees, or planets orbiting the sun. Yet, the nature of gravity is far more complex and intriguing than these everyday experiences suggest. Is gravity merely a force that pulls objects together? Or is it something more profound, woven into the very fabric of space-time itself? This fundamental question has inspired scientists for centuries to probe deeper into the mysteries of the universe. Historically, gravity was first articulated by Sir Isaac Newton, who described it as a force of attraction between masses. According to Newton's law of universal gravitation, Every object with mass exerts a gravitational pull on every other object, and this force diminishes with distance. This elegant mathematical formulation allowed us to understand the motions of planets, the trajectory of projectiles, and even the tides in our oceans. However, Newton's model was soon eclipsed by a more revolutionary understanding brought forth by Albert Einstein in the early 20th century. Einstein introduced his theory of general relativity, which transformed our comprehension of gravity. He proposed that gravity is not a force in the traditional sense, but rather a consequence of the curvature of space-time caused by massive objects. To visualize this concept, imagine a heavy ball placed on a stretched rubber sheet. The ball creates a dip in the sheet, causing smaller objects placed nearby to roll toward it. In this analogy, the rubber sheet represents space-time, while the heavy ball symbolizes a massive object, like a planet or star. This means that when we think we're being pulled toward Earth, we're actually following the curves in space-time created by Earth's mass. This revolutionary understanding leads to astonishing predictions, one of the most striking being the bending of light around massive objects. According to general relativity, light does not travel in a straight line, but follows the curvature of space-time. This effect, known as gravitational lensing, was famously observed during solar eclipses, providing compelling evidence for Einstein's theory. When light from distant stars passes close to the sun, it bends, causing the star's positions to appear slightly shifted. This phenomenon showcases gravity's ability to influence even the path of light, further illustrating its mysterious nature. Despite these profound insights, gravity remains enigmatic. It is the weakest of the four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. Its relative weakness becomes apparent when we compare it to electromagnetism, which can overcome gravity easily. A small magnet can lift a heavy paperclip against the force of gravity. Moreover, gravity has yet to be reconciled with quantum mechanics, which governs the behavior of particles at the smallest scales. This discrepancy has led physicists to search for a unifying theory that encompasses both gravity and quantum mechanics. In this quest, concepts such as gravitons have emerged. Gravitons are hypothetical particles that, if they exist, would mediate gravitational interactions in a manner analogous to how photons mediate electromagnetic forces. The search for gravitons and a comprehensive theory of quantum gravity is ongoing and represents one of the most significant challenges in modern physics. As we delve deeper into the mysteries of gravity, we are reminded of its central role in the cosmic dance of celestial bodies and the structure of the universe itself. From the orbits of planets to the merging of galaxies, gravity shapes the universe in intricate ways. It binds stars together in clusters, governs the dynamics of galaxies, and orchestrates the motion of everything from the smallest particles to the largest cosmic structures. Exploring the nature of gravity enhances our understanding of the universe and deepens our connection to the cosmos. It invites us to appreciate the intricate forces at play in the grand tapestry of existence, reminding us that our very lives are intertwined with the fundamental principles that govern the universe. As we continue to investigate gravity, we not only seek to unravel the mysteries of the cosmos, but also to understand our place within it, an endeavor that has captivated human curiosity for millennia.